Hello everyone, I am Majd, and with the help of Tamara, Haidar and Bashar, Shlash, we have put together the following presentation about different instruction set architectures, MIPS and RISC-V. We will be discussing throughout this presentation details about MIPS and RISC-V. We will also show numerous common points as well as some differences. MIPS, which is short for microprocessor without interlocked pipeline stages, and RISC-V are instruction set architectures with the same function when it comes to CPU design. They are used as a software language that builds fast hardware. In fact, they define essential data types, registers, input and output implementations, and much more. It should be noted that RISC-V and MIPS have more similarities than differences, as both of them are classified as RISC architectures or reduced instruction set computer. Before explaining the different ISAs, it is important to explain what a register is. It's a quickly accessible location available to a computer's processor for fast storage. It is used for frequently accessed data. Instead of having to access data in memory all the time, we load once from memory to register and use it as much as we need in the processor, then return the output into memory. A computer's main memory may be viewed as an array of storage elements. Each element can store a single byte, and each storage element has a unique address. The address serves as an index into the memory array. Information is stored and exchanged in groups of bytes called words. This information may vary from instructions or other data. MIPS and RISC-V find common grounds when it comes to the instruction cycle or the steps in executing any successful instruction. The first step is the instruction fetch. During this step, the instruction or piece of data is loaded from memory into the CPU's register. Next, there is the instruction decode, where the instruction is decoded by the CPU's control unit. The opcode and operand of the instruction are separated, and the opcode is moved to the appropriate register. The third step is the operand fetch. During this step, the operands needed, which are addresses where data will be read from or written to, will be loaded from memory to the appropriate registers. The fourth step is the instruction execute. This step performs the function of the instruction. The final step is the result writeback. During this step, the data is written and stored into the corresponding location in main memory.
The following set of slides explain both MIPS and RISC-V and highlight their differences and similarities. Since they are quite similar architectures, we try to be different in explaining them. By elaborating on MIPS more abstractly and focusing on the concepts, as for RISC-V, we gave concrete examples that demonstrate what the architecture can perform. MIPS is one instruction set architecture. It is a low-level language as it creates a transition between high-level language and machine language, which is binary as well. MIPS instructions, like all other, are encoded in binary, and it has 32 bits for each instruction. In MIPS we have three types of format: the R format, the I format, and the J format. All these formats are still represented by 32 bits. They're just divided differently. Keep in mind, MIPS uses 32 registers, each having 32 bits. This is called a register file, so each register has a specific number that needs to be used to access it. The R format is used when all data values used by the instruction are located in registers. The 32 bits are divided into these components. Opcode occupies 6 bits and it is most of the time 0. The RS, RT, and RD, they are the first source register, second source register, and the destination register, respectively, and they all occupy 5 bits. The shift amount, which is used when you need to shift something, it is 0 in most of the instructions, and it occupies 5 bits. And the function, which extends the opcode and identifies the exact R format instruction that we need to perform, and it occupies 6 bits. The I format is used when the instruction must operate on an immediate value and a register value. The immediate value occupies 16 bits, therefore it can be very large. The 32 instruction bits are divided into an opcode, which occupies 6 bits, an RS and RT, which are source register and destination register respectively, and an immediate value, which can be a constant, for example in add immediate, or it can be an offset added to an address, such as load word and store word. We're going to be talking about these instructions in later slides. The J format is used when you need to perform a jump to an address or an instruction. It has 26 bits of its immediate value, since addresses are quite large. The 32 bits are divided as follows. The opcode occupies 6 bits and the address occupying 26 bits. But how come is the address here only 26 bits where it should be a 32-bit address? This is because it is a pseudo address. After we modify the 26-bit address, it sends us to the correct address needed.
The following table shows the MIPS registers. As we can see, there are 32 registers numbered from 0 to 31. The first register numbered 0 is the constant value 0. The second register numbered 1 is reserved for the assembler. The third and fourth registers numbered 2 and 3 are named V0 and V1, and they are used to store the value for results and expressions. The following 4 registers, named A0 to A3, are used for arguments, procedures, and functions. The following 7 registers, named T0 to T7, are reserved for the use of temporary values. Registers numbered 16 to 23 are used for saved values. And the next 2 registers, numbered 24 to 25, are used for more temporary values. We then have the registers numbered 26 and 27 that are reserved for the operating system. Register number 28 is the global pointer. Register number 29 is the stack pointer. Register number 30 is the frame pointer, and the final register, number 31, is the return address.
One important point that needs to be highlighted is that the order of components in assembly code, be it MIPS or RISC-V, is different from machine code. Assembly code is more similar to the C code. One example would be this instruction. In C, A is set to be equal to B plus C. In MIPS assembly code, we invoke the function add, and then we place S0, S1, and S2. S0 is our destination, just like the C code. S0 acts like A, and then we add S1 to S2. S1, it would be B in the C code, and S2 would be C in the C code. After adding them, we place it in the destination register, which is S0. In the machine code, it has to follow the R-type format, which is the opcode of zeros, and then the number of the register RS, and the number of the register RT, and then the number of the register RD, and then the shift amount, which is 0 in this case since we're not doing any shifting, and the function of adding. We have 5 different addressing modes, in other words, 5 different types of instruction that we can encounter in our chosen ISA. 3 of them are used to fetch data, while the other 2 are used to address code. We know that data is either located in an instruction, memory, or a register. Therefore, the fetch data addressing modes are used to perform certain instructions with data at hand. Immediate addressing requires data to be located in a register and in the instruction, such as add immediate. Register addressing requires the data to be located in the registers, and the base addressing requires the data to be located in memory or located in a register, and then we have to either load it from memory to the register or load it from the register to memory. 2 of the addressing modes are used to address code. Basically, there are 2 ways to go to a different address when we want to get a code. One of them is branch or PC relative addressing. It uses the I format. The example is showing in the slide BEQ register T0 register 0 and, which this instruction means if the word stored in T0 is equal to 0, therefore we have to branch to the label end. If not, then we move to the following instruction. Now, how do we go to the label end? The offset stored in the I format, we take it, and then we multiply it by 4. Why by 4? Since addresses are 4 bytes away from each other. Because they're 4 bytes away from each other, therefore we have to multiply by 4. After doing so, we get this offset multiplied by 4, and we add it to the instruction following BEQ, which is PC plus 4. So the next instruction after BEQ. Once we add these two together, our result is the address of the label end. Another address mode is the jump or pseudo-direct addressing, which we use it often. The reason why it's called a pseudo-direct is because the pseudo address is just 26 bits of the full 32-bit address. We come up with the 26 bits by dropping bits 31 down to 28 of the actual address, and by removing the two least significant bits. The two least significant bits would be always zeros, since addresses are 4 bytes away.
In this code, I is stored in S3, K is stored in S5, and the address of save is in S6. We enter the loop, then we shift I to the left by 2. This is equivalent to multiplying I by 4. This step has to be done since we are dealing with integers and each integer needs 4 bytes in memory. This makes us acquire the offset needed to be added to the base address. Now we add the offset to S6 and we get the address required, which is save I. We load the content of the address into T0 in order to compare the content with K, which is stored in S5. The comparison is done using B and E. If they aren't equal, then we break. We check for inequality because it is easier and faster than checking for equality. If they are equal though, we increment I and go back to the loop.
Okay, now we're going to start discussing another kind of instruction set architecture called RISC-V. RISC-V was developed at the University of California, Berkeley in 2010, primarily for research and education, but is now being used for commercial designs. It is an open standard instruction set architecture and is designed for a wide range of uses. It can vary in length so that more bits can be encoded. In fact, this ISA supports 32, 64, and 128-bit address spaces, and each one of them includes many variations. Like, for example, the RV32, 64, or 128M that adds integer multiplication and division operations. This ISA has many types of instructions that are used to encode the many different types of RISC-V instruction. The most widely and well-known are the R-type instruction that is used for arithmetic operation, I-type instruction that is used for immediate operations, and the S-type that stores given data in registers. A given machine instruction is represented by a fixed-length sequence of bits, and this is for simplification purposes. These instructions are divided in different fields, each field having a fixed bit width and representing a part of the instructions. The first field is the opcode, which is of 7 bits. The second is the function, which is 3, 6, or 7 bits. The source register, 5 bits. Destination register, 5 bits. And the immediate, which is an integer constant of 12 or 20 bits. The total is of 32 bits. In our presentation, we'll be focusing on RV64 ISA. This ISA provides 32 64-bit general-purpose registers, spanning from 0 to 31. These 32 bits are referred to as a word. Register 0 is hardwired to 0 and cannot be overwritten. But each and every single one of the other registers has a unique name and a unique job description. The first register is the return address. This means that when we implement a function or is generated, we assume that it's traced back to the address. The second is a stack pointer, while the third is a global pointer. The fourth is a thread pointer. The fifth, the sixth, and the seventh are temporaries. That means the information is temporarily saved in these registers. They're more likely to be overwritten. The 8th and the 9th are saved registers. This is basically information that we'll be using in the future and saved as it is. The 10th and the 11th are function arguments or return values. The 12th until the 17th are function arguments as well. 18th till the 27th are also saved registers. 28th until 31 are also temporaries. The key RISC-V instructions are generally the arithmetic instructions, that is basically mathematic operations. The logical instructions that focus on binary variables whose output is also binary variables. Logical operations are the focus of logic gates in digital circuits. The shift instructions, operations that allow bits to be moved from left to right in a word. Data transfer instructions, which server is responsible for performing the transfer of data between source and sink. comparing instructions, that basically compares data, and the branching instructions, that is the act of switching execution to a different instruction sequence as a result of executing a branched instruction. In our presentation, we will be giving more information about the arithmetic operations that assemble addition and subtraction, multiplication, and division. The addition and subtraction instructions add and subtract the content of the source registers and stores the result in the destination register. In the example given, the contents of RS1 and RS2, the two source registers, are either added or subtracted and then stored in the destination register RD. We also have the add immediate instruction, where the contents of a source register that is added to a signed integer constant and then is stored to a destination register. In the example given, the sign register -15 is added to the source register and the result is stored in the destination register. The RV64 ISA includes instructions that are add W, subtract W, and add IW, which operate on the lower 32 bits of the 64-bit operand, while the upper 32 are being ignored. The multiplication instruction multiplies the 64-bit values in RS1 and RS2, the source registers, and stores the lower 64-bit of the 128-bit product in the destination register RD. This instruction can be used for both signed and unsigned multiplication, while the multiplication high instruction multiplies the signed 64-bit values in RS1 and RS2 and stores the upper 64 bits of the 128-bit product in RD. This instruction as well can be used for both signed and unsigned multiplication. As for the division instructions, we have three types of division instructions. The first one is for signed numbers, the second for unsigned integers, while the third is for the remainder. RV64 ISA also includes division W and remainder W instructions, which operates on the lower 32 bits of the 64-bit source registers.
As of recently, RISC-V seems to be on the come-up as the dominant ISA. Some main differences are that RISC-V is more modern. It includes learning and ideas that MIPS doesn't. RISC-V is more versatile and expandable as well. It is argued, however, that RISC-V puts a burden on software. RISC-V also reduces condition codes and branch delay slots, which complicate higher performance implementation. MIPS also has fixed 32-bit and 16-bit encoding, and this limits space for later expansions of the ISA. This pretty much eliminates the ability to explore new research architectures. However, in terms of acquiring MIPS CPU designs, it is very expensive and there are always copyright issues. So RISC-V was started to solve the CPU architecture and design cost problem by making a practical ISA that was open sourced, usable academically and in any hardware or software design without having to pay nearly as much as one would using MIPS. However, it shouldn't be forgotten that MIPS paved the way for the development of RISC-V. MIPS and RISC-V are mainly used in networking equipment like switches, routers, modems, NICs, and wireless APs or extenders. MIPS cores are also used in networking controllers, which are sold to companies like D-Link, and the same goes for other companies who use MIPS for lower-end Wi-Fi chipsets. Some versions of MIPS are used in workstations and the first Sony PlayStation, for example. More recent versions of these gaming consoles use newer versions of MIPS or RISC-V. The original version of MIPS was used back in the 90s in order to develop the Nintendo 64 game console. We thank you deeply for your attention and we wish you the best of luck.